Alright, so now that we're going to be dealing with the Lorentz contraction, now let's go through a perplexing question that is definitely worth investigation based on the rule that the Lorentz contraction only happens in the direction of the motion. So a record turntable of radius r rotates at angular velocity omega. The circumference is presumably Lorentz contracted, but the radius, being perpendicular to the velocity, is not. What's the ratio of the circumference to the diameter in terms of omega and r? According to the rules of ordinary geometry, it has to be pi. What's going on here? And just like the last couple questions, we're dealing with the Lorentz contraction by the Lorentz factor. So we see L shrinks by a factor of gamma. Now let's go see what we're dealing with. So as you might imagine, we have omega turning this turntable with velocity omega, radius r. Again, pretty straightforward diagram. Let's dive into the heart of this. All right, so now naively, the ratio is the Lorentz contracted circumference divided by the diameter, okay? And when we do this, what we see here is that the circumference is 2 pi r divided by gamma, because that's what we have to do for the moving object. We see the 2 r's cancel, and we're left with pi over gamma, so that just becomes pi times the square root. But we know that v is a linear velocity. We need it in terms of angular velocity, so that's omega r. So we have everything in terms of the angular velocity and the radius, but this is nonsense. How are we going to have something less than pi? The point is, an accelerating object cannot remain rigid in relativity. To decide what actually happens here, you need a specific model for the internal forces holding the disk together. So at the end of the day, our naive assumption that it's just the rotating frame is going to create a contraction is not accurate, because the velocity is constantly changing direction, and with that direction change we have internal forces that are going to have to be taken into account of, and that's not always present in these models that we have of simple things like this. So naturally we're going to have to start diving into internal forces, kind of like what we saw in chapter 11 with the radiation reaction being an internal force or internal reaction of the particle itself. So a lot more to dive into, but these are great brain teasers to break you out.